All right, I want to make the comment that the shape of the beam has no impact on the solution. For instance, let's take this crazy looking beam here that's just sort of random. And I have a 12 kilonewton load and an 8 kilonewton load. Goal is to find the reactions. Well, I don't even look at the beam. Yes, the beam is there, but when I take moments about A, I just do it the way that I always do, which is, I'm going to have 12 times 3 and 8 times 6 and by times 9. So I have all of those, and I solve for by, getting the signs correct. And then I take moments about B, it's the same thing. I have AY times 9, 12 times 6, 8 times 3. Same solution. I get AY is equal to 10.67. So it doesn't matter what the shape of the beam really doesn't come into play here in a lot of ways. It would be the same result if our beam were as straight, just like the ones we've been looking at before. So in fact, we can do the problem even without even looking at the structure. Just eliminate the structure completely. Now, we have the structure because we recognize that the structure is not moving, but when we analyze the problem, we don't need the structure. So, in fact, you can imagine that the structure is invisible when you do these problems. So, we're going to get into other types of structures, and the reason I say this is we're going to get into trusses and other types of structures, and it really doesn't add any complication. The structure shouldn't add any other complication. We'll look at what the difference is, but the end result is what we're always looking at are the forces and the distances and the points that we're taking moments about. That's what you need to focus on, not the structure itself. Okay, I want to add another situation. And in this particular case, we're going to look at a beam A and beam B. And this is beam A, and this is beam B. And if we look at these two beams, what we're going to see is that they both have a 7 kip load going down and a 7 kip load going up. And in both cases, these two 7 kip loads are separated by 4 feet. So what we have is, this situation, and we've applied it to both beam A and beam B. And you'll notice that for beam A, these two loads are to the left, and for beam B, these two loads are to the right. But both beams have the same. This is 20 feet. This adds up to 20 feet. So same dimensions of beam. All we've done is we've shifted this force, what we call a force couple, over into a different location. So I want to find the reactions for beam A. I want to find the reactions for beam B. And we just do it the same way we've always been doing it. So I'm not going to go through a lot of detail, but we take moments about A for this one. And it's going to be what? It's going to be 7 times 6 and 7 times 10 for those two. By, of course, times 20. But so I've got 7 times 6, 7 times 10. One's plus, one's minus, by times 20. I look at moments about A here, I'm going to have 7 times 13, 7 times 17, and then by times 20. Right there. Now notice by is negative 1.4 kips. By is equal to negative 1.4 kips. I get the same reaction, interestingly enough. It's an interesting concept with that. So let's do moments about B. So taking moments about B, I'm going to have AY times 20, 7 times 14, 7 times 10 for that one. There they are. Pay attention to the signs. Moments about B, I'm going to have AY times 20, 7 times 7, 7 times 3. And sign, of course, are opposite. So that's right there. And what do I end up with? AY is positive 1.4 kips. Positive 1.4 kips. They're the same. Now, if we look at the details of the calculations, we can see why. Because, for instance, that 7 times 6 minus 7 times 10, well, what's the difference? The difference is 7 times 4. And if I look here, again, 7 times 13, 7 times 17, the difference is 7 times 4, negative in both cases. So these two terms are the same. And we see the identical thing over here. Again, the difference is going to be 7 times 4 in the negative. So that is why we get the same reactions, even though the problems look substantially different. Now, so our final free body diagrams, I get that there, I get that there. And so we notice that we have the same reactions for both beams. And try it yourself. You can move that 7 kip couple. I've got to keep the 4 feet distance. I can't change that 4 feet. I got to stick with the 4 feet. But I can move that anywhere on my beam. I can move it over here, I could move it over there, I could move it over there. Anywhere on the beam, and I'm going to get the same reaction. So you can try that at home. So like I say, we call this a force couple. What is it? 2 equal and opposite forces separated by a distance. So notice these two loads are parallel. In other words, those two lines of action are parallel. And that makes it a force couple. And what we're going to do is we're going to represent this force couple in a different way. So in other words, if I take the center here and they're separated by 2, then I'm going to have 7 times 2 for this one about the center point, and 7 times 2 for that one. They're both operating counterclockwise. And that 7 times 2 and 7 times 2 gives me 28 counterclockwise. So I'm going to show it as this. I'm going to show it, and then notice the units are kip feet. Kip feet. Why? Because force times distance. So kip feet. So I have 28 kip feet. So I'm going to represent beam A in this manner with my 28 kip feet located here at 8 feet from the left end. And this one, the 28 kip feet located 15 feet from the left end. So from now on, I'm going to show these force couples with a representation that looks like that. So the way we're going to do the problem, so if I look at beam A now, this is the way it's going to be represented. and I'm going to say find the reactions. Well, now what do I do? How do I handle that? Well, now when I take the moments about A, interestingly enough, so I'm taking moments about A, what do I get? Well, this is counterclockwise, so I'm just going to write down negative 28 for that. It doesn't matter. The distance doesn't come into play here. So why? Because it sort of goes back to our original equation. So you can go back to the original equations. In other words, if we go back here, if I look at that, that is negative 28. That is negative 28. So what we're writing, so that's the way that we need to, we got to come up with the same answer. So we have to have the same result. So it's negative 28. The units are kip feet. So I don't multiply it by feet again. I don't multiply this by this 8 feet or anything like that. So it's not 28 kip feet times 8 feet, because that would be kip feet, kip feet squared. Wrong units, we can't put it into our equation. So if nothing else, you can look at the units. So I just put in the negative 28, but then I still have the negative minus by times 20. I get the same result. Now similarly, point B, if I take moments about point B, then again, I still have the negative 28 here. It doesn't matter that it's to the left, it doesn't anything. All I'm paying attention to is the fact that it's counterclockwise, and that makes it negative, and then it's 28. So, and then I have the AY times 20. I still pay attention. That's a force, not a couple, not a concentrated moment. We'll also call it a concentrated moment. Concentrated moment. Let me write it out. It's going to be a concentrated moment. So, I'm even going to give you problems with a concentrated moment. I'm not going to show them as a force coupled necessarily. I'm just going to show them as a concentrated moment, and then you solve for them. For instance, it'll look like this. I have a concentrated moment here, a point load here, and we want to find the reactions, as we always want to do. And so our free body diagram looks like this. I'm taking moments about A, and what do I have? This is positive because it's clockwise. This is negative because it's counterclockwise. So I have simply a positive 20 and a negative 5. And then I go by times 4 and 10 times 9 equal to 0. And I get by is 26.25. I take moments about B, and then again I have what? 20 positive, 5 negative. 20 minus 5. Again, it doesn't matter that it's to the left or whatever. And then I have AY times 4 and 10 times 5. AY times 4, 10 times 5. And I solve for AY negative 16.25, so I flip the force around, I get 16.25 down, 26.25 up, and I can do a couple things here to check it. One, I can look at it's one thing we want to do, what's the forces going down? I've got 10 and 16.25 going down That's 26.25, and I have 26.25 going up. That's correct. I can also take moments about this point C, this point here, and what do I have? I have the positive 20 there. I have the negative 5 there. And then I have 16.25 times 9. It's a negative, because it's counterclockwise about point C. And I have 26.25 times 5. And all of those moments should be equal to 0. I multiply all this out and add and subtract it. I do get 0, so it's okay. So as a check, I can take moments about point C, and then I should also make sure that my downward forces equal my upward force. And notice this does not come into play into a downward force or an upward force. Okay, so you do this one. We've got a concentrated moment here, 10 kilonewton meters. Find the reactions. So pause the video here and do this one. Okay, so here's our free body diagram. I take moments about A. I'm going to have 9 times 2. By times 5. And then this is clockwise, so it's going to be plus 10. I get my signs right, so the By times 5 is negative. I get By is 5.6 kilonewtons. I take moments about B. Again, I'm going to have positive Ay times 5. I'm going to have 9 times 3 negative because it's counterclockwise. And then I simply have the plus 10. Because it's clockwise. And I end up with Ay as 3.4 kilonewtons. So there's my final free body diagram. And, okay. Give you another one. Notice we have a load that is not vertical. So do this one. Pause the video, do this one. First thing we have to do is break this into components. So I've got 12 sine 60, 10.4, 12 cosine 66. This force goes downward to the right. So I have a downward and a to the right. And then I'm taking moments about A. I've got the negative 40 for that because it's counterclockwise. I have positive 20 for that because it's clockwise. And then I have my other forces. I've got By times 10. It's going to be negative because it's counterclockwise. I've got 10.4 times 13, positive because it's clockwise. And I solve for By. I take moments about B, and I'm going to have Ay times 10, positive because it's clockwise. I'm going to have negative 40 because it's counterclockwise. I'll have 10.4 times 3, positive because it's clockwise. And then I'm going to have positive 20 because it is also clockwise. I get Ay is negative 1.1 kips. And there's my final free body diagram. All right. Now, we're going to introduce a new kind of beam, in a sense, new kind of beam, called a cantilever beam. Previously, we've been looking only at what we call simply supported beams. Simply supported beams, have a roller and a hinge. A cantilever beam is different. It is not. It does not have two supports. A cantilever beam has only one support, and we can look at it as taking a beam and basically embedding it into a wall here. And it is locked into that wall, deeply embedded. It's not necessarily the way we do it, but that's the way you should think of it. So that beam is stuck into that wall, and then it's the only support. So how do I handle that situation? Well, what do we find? This is not a roller. It is not a hinge. In other words, if I had a beam that was, supported like this, and I have a hinge here, if I try to load it here, well, this does not resist bending. This is not stable. This thing is simply going to move in that direction. So I can't have that situation. I can't, it doesn't work. But if I have the beam fixed into the wall like it is here, that will work. You can build that. You can build it. Now, the way that we're going to represent that in our schematic is the way everybody does it is it looks like this. It's just fixed at the end. It's just fixed there at the left end. That's the schematic, that's the image, that's the way we're going to draw it. Now, when we come and make our cut, so now I'm going to come in and make my cut here. I can do it like that. Well, what am I going to, what do I write at the left end? Well, now I'm not making a cut through a hinge. Remember, if I have a hinge and I make a cut through a hinge, what happens if I make a cut through a hinge? Well, if I draw my free body diagram through here to make my dashed loop, what do I see? Well, I make a cut through a hinge. That means what? I have a horizontal vertical force. When I make the cut through here, I have just a vertical force. But now we're making a cut through, in a sense, right through the end of the beam here. Now what do I do? Now what do I put for that? Well, because it resists bending, I have to put in bending also. So I put in a concentrated moment. So I'm going to have both an X and a Y and a concentrated moment here because it resists bending. And it resists an upward force, it resists a horizontal force, and it resists bending. So I put these three. So that is the key to solving this problem correctly. And so the end result is that when I'm drawing this free body diagram, and now notice I have to solve for this value. So I have a concentrated moment showing there, but I don't know what it is. So I have to it's easy, simply put it into my equation. So in this particular, so let's do this problem. So I have what? For this load, I've got 10 sine 70s and 10 cosine 70. It goes downward to the right. So I have downward to the right. And of course, the vertical one is going to be sine of the angle because this is with respect to the x-axis. The horizontal one is going to be cosine of the angle, so I do that. Those are 9.4 and 3.4 respectively. Then I look at this. I'm going to take Well, I'll start with the forces in the x direction. I have AX plus the 10 cosine 70. So AX is negative 3.4 kips. Now I'm going to take moments about A equaling 0. I start here, and what do? Well, I pay attention to this sign. It's counterclockwise, so it's going to be minus AM. I just treat it just like known forces, but, I'm just going to, so I just follow the rules. The rules, nothing different. And then I've got the 10 sine 70 times 4 feet. That equals 0, and I simply solve for this AM, the concentrated moment at A. And I get AM is 37.6 kip feet. And then, well, in this case, we're just going to take the sum of the forces in the y direction equals 0. So I have my AY, and I have 10 sine 70 goes downward, so it's negative. I get AY is 9.4 kips. So here's my final free body diagram. And notice, this is a positive number. So I take that and put it there. Eliminate the AM. If it were a negative number, then what would I do? Then I would flip the... if it were negative, if I start out with AM showing like this, and it's negative, then I simply flip it around and write 37.6 if it were a negative 37.6. But since it was a positive, all I do is just put it in its place. I can do a check. I can take moments about B, for instance. You can now look at that, and that ends up to be 0, so it's okay. Of course, I have the, it's easy to see your vertical loads are up and down are equal. The horizontal loads to the right and to the left are equal. And again, I can take moments at any point here and I should get the result being 0. So if I pick a point C here and I take the moments about C, I get, 9.4 times 2. Minus 37.6 because it's counterclockwise, 9.4 times 2, positive because it's clockwise, and I get 0. So it's okay. Sometimes there is round off. If you get round off, don't worry about it, but they should be pretty close to 0. Again, I could take moments about point D. So for that one, I have 9.4 times 1. Positive. I have 9.4 times 3 positive because it's going like that. It's going like that. And then I have the minus 37.6 because it's counterclockwise. Okay, so you can try your own points. No matter what point you choose, we will have the moments being 0. So I'll do one more example here. So again, find the reactions. Here I've got the fixed end at the right side. Well, what does that do for me? It doesn't really make any complication. I have a concentrated moment here, and I have a distributed load here. So I have to, calculate those out. And again, now remember, if I put a letter next to my arrow, it doesn't matter the direction that I choose. So if I have a letter next to the arrow for that BM, I could have done it either way. I could have drawn that BM like that. But of course, it'll affect my equations. But I could have done that. So, you can choose it to be clockwise or counterclockwise. As long as you're consistent, you look at the figure exactly as you've drawn it, and then write your equations, you're going to be okay. You just have to be consistent by looking at your picture. Once you've drawn that initial free body diagram, you have to respect it and write your equations accordingly. We've done so many of these. I'm just going to let you read this. And what do you find? You find that this is our final free body diagram here. Again, how do I get this value? Well, I find the area, 1/2 the base times the height. So 6 times 3 divided by 2 is 9. And where does it go? We use the 2/3, 1/3 rule, so it's 1/3 from the fat end, which is 1, or 2/3 from the skinny end, which is 2. So again, once we have this, we can check our answer, taking moments about this point, and what do we find? Indeed, that equals 0. Okay, so here's one for you to do. Find the reactions. And what am I talking about? We're gonna have a BX, a BY, and a BM. Find those reactions. So pause the video here and find the reactions. We got a concentrated moment out here. We have a non-vertical load here. We have a distributed load there. Okay, so pause the video, do this one. All right, so we have to, use components for that. That's 25 degrees with respect to the x-axis. So 8 sine 25 is that. 8 cosine 25 is that. This is downward to the right. So I have downward to the right. I put the arrowheads. There's the arrowhead there. Both arrowheads are there. We take that as 1/2 the base times the height, so that's 4 times 6, divided by 2. Don't forget the divide by 2. If there's something that students will make a mistake on in these triangles is they forget to divide by 2. Try not to do that. So 1/2 the base times the height, so that's 12. It's 2/3 from the skinny end, so 2/3 of 6 is 4. And of course we have the 30 there. And then because I've made a cut at this location, what do I have? I've got a BY, a BX, and a BM. And like I say, the direction here, you choose it. Once I have it, I follow this. And if I take moments about B, so I'm taking moments about this point, so, what do I have when I go through I've got that's counterclockwise, so it's going to be negative 30. That's going to be negative 3.38 times 8, counterclockwise. It's going to be positive 12 times 4. And then as I've shown it, this is counterclockwise. So that's okay. If it's counterclockwise, I simply write minus BM. I solve for BM, I get negative 9.04, which means what? I'm going to have to flip the arrow around. That's all. And then I can take the sum of the forces in the y direction, sum of the forces in the x direction. That's fine with these cantilever beams, but it's a good idea to check it when you're all done. So, sum of the forces in the y direction, as I look here, I've got that going in the y direction, that going in the y direction, that going in the y direction. I put all 3 of those down into my equation. I solve for By, it's negative 8.62. Now the units there are kilonewtons. Notice the units here are kilonewton meters. So, I haven't been strict on following the units, but what do I know? This 30 has kilonewton meters. This has got kilonewtons, and the 8 is meters. So this is also kilonewton meters. And so all of the units there are kilonewton meters. And so when I solve for my BM, I end up with kilonewton meters. I guess I didn't show the units down there, so I probably should. So this is kilonewton meters. This is kilonewton, and this is kilonewton. So we can include those. Okay, I'm going to stop there.